So I can start a bit slowly. So I use that extra 1 minute before I start, so to say, to tell a little bit what is the history of having me here. I mean, people from my group have been here quite a bit over the years. I mean, some of them are here today as well. For me, it's the first time to join an OpenFOAM workshop, and I like it quite a lot. So thank you, Hrvoje, for inviting me to give this presentation here. And well, some of you might know, and I heard it was in your introductory lecture that I missed. Sorry for that one. That you are involved in our collaborative research center 1194, and that's on wetting, and it's wetting in its interaction with transport processes. So that's what it is behind today's talk. And so I'm facing the challenge of giving you a survey of several projects, so that might be in some sense a bit of a kaleidoscope that I want to look through with you. So within the CRC, we have different areas, and one area is the one with numerical projects and simulation optimization. There's also one on that. And so I will rush through those slides, but first I will introduce you a little bit to what is the philosophy of that collaborative research center. So since I collected many slides, there are also many names, and I'm happy about these young people that are behind. And so you have here the names. I mean, some of them are just PhD students, some of them are the PIs behind. So there's Hassan Ashkar, he's not here, so he is in my project, a PhD student. Francisco will give a talk tomorrow. He might be here in the audience, there he is. Myself, then Elisabeth Diel, she's from the optimization project. Mattis, Dirk Gründing, he was a former postdoc, now he left academia, unfortunately, I have to say. Florian Kummer is one of the PIs. Tomislav Maric, I think most of you know Tomislav. Holger, he's here. And Suraj is also here, gives a talk tomorrow. And then there is Matthias Riegmann. And then the coordinator of the CRC is Peter Stephan. So I'm the vice coordinator. And then I have a colleague from mathematics, Stefan Ulbrich. He is doing optimization. So these are the people behind the slides of today. But before I really go into the different projects, I want to transmit a little bit of our idea behind. So motivation is, of course, that wetting has lots of applications. So you have production techniques, for example, and we are looking at that, coding and printing techniques. And as usual, you want to make things faster, cheaper, better, and so on to enhance the process. We are looking at energy processes, heat transfer, for example, cooling, spray cooling, and this kind of stuff, where also wetting is important. And again, you want to improve basically densities of transfer fluxes. And then in process engineering, you have lots of application in microfluidics, because they are, of course, because of the different ratio of length scales, capillarity dimensions are really important. And then you can look into membranes for separation technology, and then you want to enhance, for example, rejection rates and so on. So that's the motivation. And as I already indicated, for us, it was important to look at this interplay that was bringing this project to success concerning the funding. And so the starting point is simply in quotes, the wetting itself. So it's hydrodynamics. You put a liquid in contact with a solid and want to understand what happens. But even there, if it's dynamic, I would say understanding is still limited. The modeling is difficult. And predictive simulation, I don't really know if we can do it at the moment. Let me take 1 minute for explaining a little bit what is part of the problem. I mean, if you have worked with wetting and want to do numerics using, let's say, sharp interface modeling, I mean, what do you do usually? You take two-phase Navier-Stokes. I mean, we are used to having that around for many years, a few decades. And then you say, okay, the interface, in addition of all that, has to touch some boundary, and you prescribe a contact angle, and you make it probably a function of contact line speed, let's say. And then, of course, what is well known and came up in a famous paper by Hugh and Scriven, then you see, okay, how can a contact line move if I have a no-slip condition? So that is so-called paradox. So you have to relax the no-slip condition. And then what people usually do is they go for some Navier slip, and I will elaborate a little bit on that later. And then people say, okay, now we have a model. Now, what we did in my project in the first funding phase, we looked at the kinematics of such a vetting process quite a bit. And from pure mathematics, really with the proof theorem, I can show you if you have a solution that you ask to have gradients that are continuous up to the interface and up to the contact line, it will not work. This model, taking two-phase Navier-Stokes, adding this condition, will never allow a droplet to reach its equilibrium shape. There is an intrinsic problem. So this modeling is actually not far enough, not deep enough. That's part of what we want to understand more. But the main point here is to put more complexity, because you have interplay. You have this interplay with heat transfer, mass transfer, and you have complexity in the materials. Huh? The fluids will be mixtures, non-Newtonian behavior. The surfaces are more than just a flat planar surface and so on. And this is what is behind. And so let's move on, if I can. Yeah. So the overall philosophy, and this is not something very specific, of course, you have seen it in other talks, I'm sure, is to make a bridge between several ways to bridge things. So one is from fundamentals to applications. So there you see some forced fast de-vetting process in some small scale experiment. And then here we want to go to some gravure printing process and want to understand how to fill these little caps and how to get away with if you have too much of liquid, and you usually you'd have to take it away with some doctor blade and so on. And so we want to bridge this fundamentals to applications, and we also want to use complementary methods to do that. So both on the experimental side, we don't want to have just one measurement technique. We want to have diversity and see when is which one the better one, how can we compare, have some mutual validation and so on. The same with numerics, and I go into more details on that in a moment. And then, of course, we have to bridge length scales. I mean, it goes down to molecular length scales. Then you have some intermediate micrometer length scale, and then you have capillary length scales, let's say of a few millimeter, and then you're going up, as you all know. And to bridge that scale is, of course, a very large, huge challenge. And well, it's hard to have some, I would say, some generic way to bridge that, but still we want to do something. This is just one slide on the part. I'm not talking about any data. So these are the projects from project area A, and forgive me to not have translated everything to English. So there are lots of experimental projects, which we called generic experiments. Probably more proper English would be fundamental. So it's not yet some application. It's really to look at something in all details and try to get local measurements and to provide understanding, and also to provide some data for modeling and for numerics to compare to. And then we have a project area C that I completely have no slide. That's really some application stuff. And then we have the numerical parts. And well, objectives are pretty clear to all of you, I would say. I don't have to say much on that here. We want models that are physically sound, and actually the long-term goal would be to do predictive simulations. And then we want to have validated codes, of course. And as I mentioned, we have these fundamental experiments. We have something called a guiding measure in these collaborative research centers. And so we have two specific configurations where we do very simple, so to say, simplistic experiments and have measurements. And we all have to look at that if we do numerics. And then it was a strategic idea or decision also that at least from funding phase 2, and we are now in funding phase 2 on, we want to have all the methods using OpenFOAM. So we want the different methods to be available, to be probably to be combined into hybrids, and to have some kind of method adaptivity. So look at the best method and don't really try for many years to take your favorite method, which is not appropriate, and try to make it work. Yeah? I mean, we had experience of that type long ago, and you know, it takes time, but it doesn't bring you sometimes to your goals. And then finally, the idea is to have overall descriptions where you go up to enhanced design. So we want to tell the guys from printing, you should change your doctor blade in this way, or use that gap height to have optimal results. So now let's focus a bit on this numerical project part. So OpenFOAM as the platform. And here is just, I try to produce a survey type of slide on the different approaches that we are using. I mean, not all of them are already inside a single project, but they are, the people involved are having this in their toolbox, so to say. So most of them use sharp interface modeling. So we have interface tracking, going back to the PhD work of Chelko Tukovic, it might be also somewhere here. And Hrv was the supervisor of that. And so we are working with intertrack-foam, and then of course VOF, and you know, there is this algebraic way to transport the phase fraction field, and in Darmstadt we also have some extensions where there's some reconstruction in the group of Peter Stefan that was done long ago. And then geometric transport is what with Tomislav Maric we worked a lot on this VO-foam, as we called it, with a full three-dimensional computational geometry behind to compute accurately and efficiently fluxed volumes. But then we also are now relying on interisoFoam, where you basically can make use of Reynolds transport theorem to use actually the surface to compute the change of a volume. So that's a nice idea, and we are applying. So up to here, that was the survey part. And now, well, I have to tell you, we are still facing now 40 slides. So, I mean, I asked the people, of course, young people, give me some slides. I gave some skeleton, and they gave me slides. And now I filtered some of them out, but still, there are quite some slides. And I have to rush through some of that. Let's see. So the BO1, that's using volume of fluid. Idea behind was if we want to go to mass transfer problems, we want to have really conservation of phase volume. Otherwise, if you want to change volume because of mass transfer, it's hard to know what you're doing if your method is losing volume anyway. Yeah? So that's why we said, and also with topological changes. Yeah? So the colleagues want to have two droplets attached on a surface and let them coalesce across the contact line. And we want to look what if we can reproduce. And that's why we said we need one project doing VOF. And as I mentioned here, we kind of switch to interisoFoam. And let me only go to this underlined stuff. So of course, we want to have the dynamic contact line treatment, yeah, let's say improved or adapted to our needs. Curvature, as usual, is always the problem. Have precise curvature calculation. And then to achieve second order interface reconstruction. Also, here is the important stuff, near walls. Everything that you can do nicely inside the bulk phase, we also have to do it at the boundary, because there is the contact line and there is where the additional physics takes place. So, well, I can be fast here on that, I would say, because that's, I mean, published work from other people. I mean, Rönnby, Scheufler, and also Hrvoje Jasak, I should mention here on interisoFoam. So it's a geometric method. As I said, you reconstruct the interface to take advantage of Reynolds transfer theorem. That's what you do. For reconstruction, yeah, you can do a kind of coupled procedure to find out normals and at the same time compute signed distances. And having that, you can also look in normal direction and build up a height function using parabolic fitting locally, and then you can have some curvature computation, but still, as I said, curvature is always a problem. I mean, it's a second numerical derivative, and then that tells you that you have problems. Any noise you have will, of course, be visible in the result. For the contact angle treatment, we use some ghost cells that are next outside of the domain, so to say, using some artificial interface points and putting them there that you match the contact angle that you should have because of the contact angle modeling. And then that information goes into this reconstruction of the interface with the signed distance function calculation. And that's the way to implicitly make sure that you are meeting the contact angle. Now then, of course, comes the question of verification. And here we could use what I mentioned, this kinematical analysis. Here it's pretty simple. If you give me a velocity field and you give me a normal vector, and then I can compute, of course, a trajectory. And along the trajectory, you have a nice equation telling you how is the normal evolving when you go across that path. And this you can then, for certain velocity fields, do actually analytically. And so we have a reference solution for a test case where we have a droplet, a spherical cap, and we move it around a bit, shake it a bit, deform it. And so then we know what we would have to get, and then we look for grid convergence. And yeah, it looks okay, but we have still some problems. You see, we are not yet at the analytical curve. So even here, we're still facing some minor problems. So with this, at the moment, we have first order convergence. Then we look at standard droplet spreading case. You put a droplet on a planar surface. You let it settle down with the contact angle given, a static one. You look at the shape, the foot length, and the height, and you do the same to get more complications also with meshing. You put it onto a solid ball, and then you look actually what is the, for example, what is the height of this droplet adhering to the plate if you change gravity, which turns out then to change the bond number in the non-dimensional form. And here also on the solid ball, you can look at the height that you get of the settled droplet and also at the contact radius. And that looks pretty nice, although we have some findings also that we see appearance of wisps in the bulk. And if we go to extreme, I would call, or rather extreme contact angle ranges, then we also see that's quite a challenge. But otherwise, we have a nice agreement. And now here at the moment, I can only show you work in progress, no real simulation so far. That's what we want to do. We want to let a droplet slide down an inclined plate and then hit an obstacle with full resolution. So the obstacle is really there as a geometrical obstacle, and we want to see how is the droplet getting to be pinned at that obstacle. Yeah? One problem we are solving hopefully at the moment is, I mean, if you start from a spherical cap, you have to compute for a long time to get a nice shape of a droplet going down. So we would like to have a better initial value, and we take it from experimental experiments. So that's where it's very helpful to have these partners in the CRC. And now the question is, yeah, well, get that as an initial profile and then let the simulation hopefully run. So we have some preliminary results, but they are not so convincing that I wanted to show you. So we still have problems. I mean, you all know that this is challenging stuff and it will not work on first try. Next project, Matthias Fricke is now since a few days the PI, because there was a change because Dirk left, and Suraj, who is here, is a PhD student. Tomislav is also involved, and we have also Chelko involved, and we have another Mercator fellow, Joel de Koning. He's doing molecular simulations, and he knows a lot about wetting on the molecular scale, and he is also behind as a partner for discussion, let's say. So here with the inter-track foam, we have the nice opportunity to also solve PDEs on the interface, because we have a surface mesh coming with the method. And this allows to go for surfactants on the interface to solve surfactant transport equation. Then going down, something that the colleagues from material science like, they put polymer brushes on the surface, and that changes the wetting. It makes it adaptive. So if the droplet is touching the polymer brush, that is reacting, so we have additional physics. And then there is a very elaborate model that is going back to Yuli Shikmozaev, and that is taking much more thermodynamics into account. It goes for accounts for surface mass. So you have mass per area, because the interfacial area, this very thin layer, has a different thermodynamic state, and you put it as an axis variable, you put mass there. And that's the point where I need to show you something. So I borrowed that from the Porter's Lush. So what do you think how wetting works? I mentioned this paradox about the Navier slip condition. If you say Navier slip is what is doing, then you are actually believing the following, that the droplet, well, that's now replacing a droplet, it will just slide. That what you believe, yeah, because you allow it to slide, because you say this is what happens if it's sliding. But if you talk to people like Yuli, I talk to him quite a bit. I mean, what these people say is wetting is the following. Yeah, this here is the wetted part of the drop, and this here is wetting, or it's de-wetting. So this is the process. What at least that's many people or some people say that's what you have. So you are putting stuff from a normal direction to the surface, and then you can also put it back again. But then you already see you cannot have the standard condition of impermeability. You need V times normal to be non-zero. And that is not the standard model. And that's another world of models, and they are much more complicated. And we hope to do something with the inter-track form on this interface formation model. And then there are some the other direction, very effective modeling, where you have some, even probably some heuristics. You are lumping a little layer here to something where you say, I have some model that is not necessarily so fundamental. I want to do it with a numerical simulation. And then again, it might ask you to solve a PDE, this time now on the flat surface. And that's what you also can do. Okay, so this is what it's about. This I will not read out, only say that here, that is the nasty condition. I mean, that's what everyone is using. Contact angle is a function of capillary number, and here is the contact line speed. But as I said, that's too short-fetched, so to say. Okay, only very few words, ALE interface tracking. So you are having this additional reference frame that you are using. And so you are moving around the grid, but the velocity that you use for moving it around is not the flow velocity. And you have some way to compute a velocity that makes more sense, so to say, because it follows really, it adheres to the interface. But away from the interface, you can have a very smooth field that actually is not doing much. So here, cells are not moving a lot. And there is this famous control point algorithm, and we are still sometimes puzzled about it a bit, but it works nicely. So you start with the volume fluxes that you compute, and you have an auxiliary step where you put control points and move them, and then you go to the movement of the vertices, and then you have one time step of motion of the interface. One very prototypical and simple looking but very rich example is just a capillary rise. I mean, this tells all of you something. You have this communicating tubes, and you see the different rise heights. So for us, that's a very convenient case. Why? We can do it in 2D, so that's much more easy and fast, of course. We can do it in 3D with different cross sections. There are a lot of reduced models. I mean, there are classical ones that are almost 100 years old and still work rather well. Joking. Different rise regimes. I will show that in a moment. And then it's a door into more complicated systems of application relevance. Yeah? So that made us aware that we should go for this very simple case. And you see, if you have, I mean, this is just a simulation with intertrack foam without oscillation. But if you have the right parameter regime, then you see also overshoots and you have an oscillation. And what we find, and we did a benchmark with several codes, what we find, the slip length is, of course, a very important point here. So again, we are back to the Navier slip condition. That is, I would say, pretty artificial, but you need some relaxation. And then what you see is the slip length. It is doing something a bit nasty. So if you have a large slip, you have this overshoot. And here we have a classical model that goes back to this classical work by Boussanquet in almost 100 years ago. You have the so-called Urin's height, that is the rise height if you just look stationary. It's a bit overestimating. It's a way how to define where is the height really. Is it the lower point of the meniscus? Is it some intermediate value? If you look at the lower point, you should correct the Urin's height. And then you see a numerical simulation with a large slip has this oscillation. Now we make the slip smaller by a factor of 10. You see it's severely damped. And actually, this tendency goes on. It even goes on so far that I would say if you want to do it with a molecular slip, I mean, nobody can do it because of the resolution problem, but it would not go up at all. Yeah? And that tells you, okay, I think we have a problem here. What is also nice, and it's work in progress, and that's where Joël de Koning is also involved, there are really recent enhanced ODE models. And what we found is you have dynamic wetting there. So you have more than one ODE. You You also have ODEs for the contact angle, so to say. And then what we can do is we can use the DNS to calibrate these ODE models, and then they work pretty nicely. And that's one hope, to bridge the scale to go down to actually much more realistic slip lengths, and then to give an answer to the question, is the model usable? Yeah. Next one, Holger is in charge of it, and Francisco, we will talk tomorrow. So again, I can be a bit fast, I hope. It's to couple the different scales, and here is now the question, can we couple it to the molecular scale? And our idea was, together with Holger, of course, if we use diffuse interface, that should work better here for coupled hybrid simulation. Why? Of course, if you want to couple these two approaches, you need an overlap region, something where you have a matching. And with sharp interface, it's very hard to do. I mean, there is no region for a match, actually. So the idea is to use the diffuse interface and have some overlapping region where you couple molecular to continuum scale. And of course, there is, or hopefully, or not neither, of course, no, hopefully, I mean, nicely, there is this hack approach available, and that's part of the project. One of the long-term goals to look at this coupling. And yeah, here are more pictures. I don't have time to go into that. And with this diffuse interface, you can look, of course, into the droplet and see the dissipation. And here are more equations. Cahn-Hilliard equations, where you have a free energy functional, you have a chemical potential, and you, of course, have the species equations, but you need more. You have to couple it to Navier-Stokes. Although I love equations, being a mathematician, I will not read that out to you. So ask questions or approach also Holger, of course, about that. And then more to the results. So first, of course, validation. So stratified shear flow is something where you have an analytical solution where it works pretty well. And then they looked at this three-phase Rayleigh-Taylor instability to really make sure it's working for more than two phases. So it's a general approach with the idea to have n phases, actually. And here it also turned out, as it should be, that this upper interface is not acting on this lower one force for, let's say, for the first initial phase of the process. More verification, validation. This is this capillary rise with overshoot, so the oscillatory regime. And you see a match with another VUF solver we had before, free surface 3D, that's fully Cartesian code. And dinosaur, but a good one. It gives you also nice results, but only if you have a very cheap mesh. Yeah? Then for spreading and sliding droplets, you also have a very good comparison. And you can then look into capillary forces at the contact line. You can look into dissipation. And this is the way that you want to use the DNS to have a magnifying glass to look into the finer details. And then when it comes to applications, so there is a nice collaboration with Professor Bothe from Max Planck Institute for Polymers in Mainz. So they do lots of experiments with sliding droplets as well, looking also at electrical effects. And they came to Holger asking a question of, we need some effective mass. We cannot use just the weight mass. For our modeling, we need an effective mass that takes into account rotation inside the droplet, and that was able to give that to them from the DNS, so to say. And then here on that side, you have a droplet that goes down on a periodically heterogeneous, with heterogeneous wettability on such non-homogeneous surface, and you see, of course, the droplet reacting to this differences in contact angle, and you see some periodic pattern, of course, developing. So yeah, so you see that with diffuse interface, you can do a lot here with this phaseFieldFoam that Holger and co-workers developed, and current stuff that Francisco is doing. He already did some simulations where he put a single droplet onto a fiber and did some validation work that turned out to be very nice. And now what is currently on is to go into more realistic fiber mats and to have a workaround or let's say, a working flow to produce this fiber mats in the computer. Yeah? So you have some tool that's playing Mikado for you, and then you have to get some mesh, and here the workflow produces you an appropriate mesh, so that the next step will be to put now droplets into this structure and see how they are moving around because of capillary forces. Even more to come. So I showed you this doctor blading, and we come to that in more detail in a moment. And here are some first results in 2D simulations. So the question is, you put the ink here. Let's get that movie started. So you have here the ink. You put the ink into this little cups, and you want to remove superfluous ink with this blading process. And then you have a certain idea of how thick the film should be behind this doctor blade. And of course, wetting is important, and you have here creeping up of the contact line behind. And the geometry is, of course, important, and so on. And these are the first simulations that are now hopefully useful to tell these colleagues what to change in their apparatus. And that brings me to the next sub-project that's from the colleague from optimization. So they are really focused on this doctor blade process. They are really doing math, so they also do some analytical stuff. You will see something in a moment. But then they want to develop an enhanced code based on interFOAM. They called it interisoFoam, actually, where a joint code is added so that you also have gradient information available for let's say up to state of the art optimization. So first of all, you have to be able to do simulations for the process. So here are two movies. This one, the first one, sorry, is experimental. Let's see if I can start that one. So you see a droplet sitting on a cylinder, and then it touches now this doctor blade. You see a thin film going across the doctor blade, and you see the rejected part of the droplet, so to say, and it takes a while until all is sucked under this doctor blade, and then you have this film formation. And the same thing then done with basically it's basically interFOAM, but with different geometry. So not with the cylinder, but just with the planar geometry. And it's I would say a qualitative way of validation to see we can look at the film height, for example, and we see there is a good agreement. And we already there was some finding that that you can have really that air gets into the gap, and that can then lead to rupture of the film, which you usually don't want to have. Okay, so that was one step. And now about the control. Now to control two-phase Navier-Stokes, it's a challenging thing mathematically, but it's also challenging experimentally. And the first step usually is to apply a volumetric control. I mean, this is nice to start working, but it's a bit hard to do that in the experiments. And you have to apply a volumetric force. So you can try to play with, I don't know, electric fields or whatever, but usually you have boundary control. So this is the step before. It's a volumetric control. You also can play around with the initial value. And yeah, this is how you look at these things if you do mathematical analysis. You see some Sobolev spaces, the stuff that I like a lot, but I will not torture you with that. So, but they can prove actually that the map that takes the initial velocity and then this volumetric control and maps it to the resulting velocity field in certain spaces, the pressure field, and also the height of the film, that this here is well defined and is continuously differentiable. And that's, of course, an important knowledge. If you want to do optimization for something not differentiable, well, sometimes you can do if you have some lower semi-continuity, for example, but usually if you want to apply gradient methods, you need the differentiability. Okay, why do I show that to you? Because I want to transmit that we are having there a CRC with quite some mathematics involved. So we want to have the eyes of mathematician with their specific view also involved, looking at it with some mathematical rigorosity, and see that it hopefully then also gives additional understanding. And I think we can prove that that's the case. Now here I'm a bit short on what to say on that, but of course this intersense-foam where you have the adjoint equations added has to be placed inside an outer loop, and they use Matlab here for that outer loop. So to actually then compute the Jacobians and do the real optimization loop. And what they did for a starting problem to look at something concrete is you give actually the height of the film as the target quantity. You want a certain height, a certain distance away from the blade, and you can adjust here the height of the gap. So that's what they did, and here are some numerical results, and you see that the gap is then adjusted to really get that height. So that's what you expect to have such kind of results. Last but not least, that brings me to the last few slides. And that's a project where also Hrvoje Jasak is involved. He is a Mercator, as I mentioned, Mercator fellow. That's the concept of the German Science Foundation to get foreign people involved in such a collaborative research center. And so the idea is, it's a long-term idea, I would say, to put discontinuous Galerkin methods also into OpenFOAM. And here we have a group, and that's a group of Martin Oberlack and Florian Kummer, who is now permanent there. They already spent many years to develop two-phase discontinuous Galerkin method using methods from immersed boundary and multi-phase approaches, so to say. And so there is lots of manpower already inside, and that's why we don't want to dismiss that. And that comes under the name of Bothe, a bounded support spectral solver. And the idea of DG, I don't know if I have to say much on that. So well, it's if you want to start, you can start from finite volume. And what do you want to change? You want to change the order of approximation within the cell, make it linear or second order or even higher, but still allow for jumps at the cell faces. So that's an important difference to finite element, for example. But the similarity is you use weak formulation. So there are test functions in the formulation. You are able to throw derivatives to test functions. That is also something nice if you have to deal with curvature. You can also try to throw one derivative onto the test function. That's what finite element people do a lot for two-phase flow. And okay, so you have a higher degree, higher order of accuracy. And you can also, because you have jumps here, and actually you can use first order Riemann solvers to deal with that jumps. And actually I'm just doing karaoke in a way. So I was told by Florian, you can just use upwind, and that's okay to keep the higher order of your DG scheme. So here, that's a nice picture. I mean, that's a ninth order representation on a very coarse mesh, and you see what you can still do because you put now the order as your additional parameter to tune it to make such steep gradients here possible. So at the moment, our one way, there's another way that is run by Hrvoje, but one way here is to take this Bothe code and to create an interface, to implement an interface to make this available to OpenFOAM by such a software interface. So now here I'm the wrong one to say much more about the details. So if you have questions, please contact these people or contact me and I will give you the contact information. What can they do with the DG approach? So here is one prototype example, and that is going back. I mentioned this light configuration, this guiding measurement, very simple experiments, so-called Wilhelmi plate. You take a plate, you pull it out of a basin of liquid, and then you pull out also the contact line, and you see how it changes dynamically. And now on top of that, remember, we want an interplay with other transport. On top of it, you put heat transport, and while putting up the wall, you heat that. So now that's what's happening. Now you push up that wall and you start to heat the wall. You see the contact line is dragged up. But then at a certain time, the heat is now going into the full bulk phase, so to say. And now you have strong evaporation. and that pushes back the contact line. And then you are reaching a new equilibrium where evaporation and the motion of the heated wall is now in an equilibrium. Okay, so that's the end of this guided tour. I hope it was still bringing you something, although it was quite some kaleidoscope. And I thank you for your attention. I look forward for discussion. Thank you.
Thank you, Dieter, for that. That was really inspiring. Now I know why you never sleep and why I worry so much. So do we have questions from the audience, please?
Don't be shy. I have many people here that can answer them.
This is going to sound a very stupid question. What do we know about the surface flow on the surface of a moving droplet?
Yeah, that's not a stupid question at all.
It just comes from the seeing things as a young science student at school, watching droplets move down, and you always got the impression it was almost like a caterpillar track rolling down.
It's about rolling motion
versus
sliding motion. And well, I mean, at the moment, I would say it's kind of religion. So there are believers for rolling motion and there are believers for sliding. What we plan to do with the printer, guys, to print a mesh, a Cartesian, I mean, just some marks onto a droplet, onto a pretty viscous droplet, and let that then go. I mean, we did our own experiments. Dirk Gründing did experiments where he created a little colorful, I mean, little color mark on the droplet and let it go. And you nicely see how it goes under the droplet. At the same time, you see how this little blob, this little color starts to enlarge. This is something we don't understand because diffusion can never be so fast. So there seems to be a surface. That's why I'm coming with that. You asked the question about surface velocity. There seems to be a more complicated surface velocity that we are actually not aware of. And that's why we want the printers really to put a grid, print it and let that run and see how that grid deforms. But that's, I hope I can tell more about it in a few years. But it's the contrary of a stupid questions. And by the way, there are no stupid questions anyway. There were more.
Thank you for the interesting talk. I have a question about the coalescence of two droplets. Is it possible maybe in a future to face this problem? Because if I see droplets when it's raining on the glass of the car, I see that when two droplets coalesce, they move very faster. And then I think I completely didn't understand the fact of the slip and no slip condition. So you avoided the no slip condition and you made the droplet free to slip over the wall, or you have made a mixing between these two conditions? Thank you.
Okay, so I will try to answer one by one. So let's go backwards. So we use Navier slip. So we have a slip length, a finite slip length. So we go as all people usually, or the majority of people, being aware that slip is not the final answer. We still use it because we cannot at the moment do a rolling motion, because it would require more complicated models where you can touch the boundary from normal direction in finite time. So that means this motion where like a tank is running. So we use what we can do. So okay, that was one question. The other was about the coalescence. My impression is the free coalescence is much more complicated. So the contact line coalescence I think this is seems to be process that is more forced. So what I mean is that if you put two droplets together, you can have them almost in contact for quite a while, because the gas film in between needs to flow out, and until the thickness of this film reaches a scale of a few angstrom, yeah? So that van der Waals forces can really open the phases and make the contact. And then we burned our fingers trying to do predictive simulation on that. But there are some people, let me mention James Brittles, who is really far on that track. But now if you have the settled droplets, it's the contact line that touches and there is no film in between. And so I think this is much less demanding to have the two contact lines merge. And then of course you need a VOF, for example, or level set to allow for topology change. But I think this is much less demanding than the free bulk coalescence.
Could you comment about a problem of two, let's say a sandwich between two solid surfaces and liquid inside? These solid surfaces are coming close to each other, so the meniscus is becoming smaller and smaller. So there is a paradox here that the contact forces go to infinity, or
so I have to ask, so you have the gap, two solid plates, let's say,
droplet,
and in between there is a meniscus, so you have two phase in between, liquid gas, or
two phases in between.
Okay.
Yes.
I mean, okay, so you know that the forces have their range where they are being able to have an impact, and you have small scale forces that give you contact forces that you model as surface forces. You have the bulk forces, the body forces, and you have intermediate forces. And if you are close to interfaces, these intermediate forces get into play, and you have to start modeling additional forces, I would say. And with solids, I'm not so much expert, but you have, of course, disjoining pressure forces that you have to put in your model. I mean, I'm openly saying I'm always a bit puzzled which of these forces is already inside, because we have a stress tensor anyway. So how much is already modeled and how much do I have to add? I'm not a true expert on this question, but I would like to learn that. But I think if you push that more and more close, at some point you have to change your model. And that gives me a good opportunity, because then usually that's the point where some people jump up and say, yeah, you cannot use continuum modeling anymore. And this is something I don't like so much, because I would say we have already continuum modeling used for surfaces, also with tangential flow process that works pretty well. So you need to have some local equilibrium, and so some neighbors that can really exchange energy and so on, and entropy. So, but even having neighbors on a two-dimensional manifold, that's already enough to be able to have a local thermodynamic equilibrium, so that all these thermodynamic fields are defined. So I would always be a bit hesitating to say I cannot apply continuum physics. I mean, that's a very mighty tool that you should not throw away easily. But to have more forces, this is definitely the case that you have to think about what are additional small or medium scale forces that I have to put. But don't ask me how to do it precisely. This you have to find out in your case if you have a problem of that type.
Are there any more questions?
First of all, thank you for the talk. It was really interesting. And can I have a follow-up question on the modeling exchange? Because usually with wetting, right, and simple wetting, you can use the film equation and everything is nice and mostly well behaved. And if you really want to understand the contact line motion, people tend to try to use molecular dynamics or something like this, so you really can see how what the molecules are actually doing there, because at some point there is the molecular level, right? So you think one can overlook that and go with a
say the last part again.
you think one can overlook that and go with a model instead, volume of fluid or
Okay, I'm not sure. You can correct me if I get it wrong, but and it gives me a good chance. I'm not saying that you should not use molecular pictures in the modeling. Yeah? You should not do continuum physics without looking at molecular scales. And so what we have with the discussion with Joël de Koning, I mean, he has the contact line inside this bunch of hundreds, thousands of molecules, and you can nicely see how that contact line is moving, and you can filter out a continuum scale contact line, and you can check the laws that you want to apply and so on. So this, I mean, continuum physics will never give you the final closure. It gives you a framework. You have a second law, you have an entropy principle, you have a very nice framework for consistent modeling, but it never gives you the final PDEs. That would, I mean, it would mean that you don't need materials with all the differences. And of course, it comes to a point where the different materials have the different characteristics. And then you need statistical physics, you need molecular information. Sometimes you go with some heuristic stuff. So it's really the combination. I hope that answered a little bit. So thanks for asking, because otherwise it could be a bit wrong picture that came up. You need all of that together.
Well, thank you for that, Dieter. I will stop the questions here. So let's thank the author one more time. Coffee.